Hello friends, welcome to lecture 8.2 on the topic of orthogonal scaling function basis and multi-resolution approximation. So, we are in the 8th unit, which is on discrete wavelet transforms, and this is perhaps one of the key lectures that you should watch out for apart from 8.1 and then the one that is coming next, which is 8.3, because it really establishes the base for discrete wavelet transform, the theory and also the implementation, right. And also it establishes a connection between the wavelet functions, scaling functions, multi-resolution approximations and ultimately the filters that we are going to use in implementing DWT. In this lecture particularly we are going to talk about approximations at a scale. And you must have started noticing this even in 8.1, that the moment we started looking at DWT we have begun to talk about approximations and so on rather than time frequency analysis, and we will understand why that is so. And then we will look at the multi-resolution approximation equation, the basic equation that one encounters in multi-resolution approximations. In this and then finally, we will move on to the formal study of multi-resolution approximations. In that process, we will also take a quick review of what is an approximation, orthogonal projection and so on. So, before we really dwell into the math, let me make a few opening remarks. The first thing that I want to mention, which is not really listed here on the slide, is a point that I just made. When we were looking at CWT, we were talking about time frequency analysis and using complex wavelets and so on, and talking less about approximations. It was more about time frequency analysis. Of course, we did talk about singularity detection, regularity measurements and so on, but not so much about approximations. Now, the moment we have switched over to DWT, we are talking about approximations and so on. The prime reason is, as we move from CWT to DWT, as you must have noticed even in the previous lecture, we start to generate basis functions for spaces, the real number spaces or complex number spaces and so on, whereas that was not the case with continuous wavelet transform. The analyzing functions that we were using in CWT really do not generate basis, but in DWT we have this great opportunity of generating basis functions, in particular orthogonal basis functions, and they are ideal for generating approximations. More interestingly, they are ideal for generating what are known as multi-resolution approximations, and that we shall understand both with an example and with the theory later on in this course. So, the other points that I want to make ahead is the coefficients that we compute. Now, we talk about coefficients just as the way we talked about Fourier coefficients and so on. So, the transform that I compute with a wavelet essentially yields me coefficients, and when I am computing these coefficients at a scale 2 power m or at a level m, what they essentially do is they are capturing the details in the signal at that scale. Okay. And of course, here scale refers to resolution. So, that is a more appropriate term in DWT. Of course, scale will always denote a frequency band, but in DWT it is always a good idea to keep this scale versus resolution relationship in mind as well. So, as I am going up the scale, I am looking at coarser and coarser resolution. So, the analogy of a map, geographical map that we had discussed long ago in one of the introductory lectures really applies here. So, as I am going up the scale or up the level, I am actually looking at a coarser picture of the signal, and what these wavelet coefficients give me are the details that are left out or the details of the signal at that coarse particular scale. And the second point is that the DWT coefficient at any level m are actually spaced 2 power m Ts apart. Now, what does this mean? So, Ts is the sampling interval of the signal. As I am moving up the scale, what is happening? I am actually losing out on the time resolution. that is what this means. So, if I move from scale 0 to scale 2 or level 0 to level 1, then the spacing in time falls off by a factor of 2. So, I have samples the sample signal with a sampling interval of Ts, and then as I move to DWT, as I look at the DWT coefficients at scale 2 or level 1, then the spacing between the coefficients now is 2 Ts, and then at level 2 it is 4 Ts and so on, which means I am losing out on the time resolution. At what cost? I am obtaining now better frequency localization. So, that time frequency tying is always present. The only difference is now it is in the background, and we have talked about it quite a lot as to how wavelets really sacrifice on the time localization to get an improvement over the frequency localization. And the third point is, which is very important for multi-resolution approximation, when I look at the wavelet coefficients at two different levels, what is the difference between them? Well, when I am looking at the coefficients at a level m, some level m, they contain the details that are necessary for me to move to a finer scale, which is at m minus 1, and construct an approximation at that level, right. So, it is essentially what you are doing is what we are saying here is, as I move down the scales, or let us say I move from coarse to finer, and I am collecting all the details, those details become necessary to construct approximations at a finer scale. All of it may be a bit abstract for us right now, but as the lecture unfolds and we look at a few examples, things become a lot more clearer, hopefully. So, let us begin with a recap of what a discrete wavelet transform is. The dyadic discrete wavelet transform, we will not use the dyadic prefix all the time, it is understood that it is dyadic. Essentially S is 2 power m, that is what dyadic means, and that is given by the equation that we have seen in the previous lecture. It is simply the wavelet transform, the standard CWT, but now with evaluated with the specific wavelets which are now positioned at dyadic scales and translations proportional to these dyadic scales. At this point, that is in equation 1a, the wavelets, the family of wavelets that are generated by spanning m and n, that is when m and n take on different values, they are not necessarily orthonormal. However, if we design a wavelet such that this family of wavelets are orthonormal, then as we have seen in the last lecture, the reconstruction equation or the synthesis equation and the energy decomposition equation take some very nice forms. Notice and recall from lecture 8.1, whenever I use an orthonormal basis, then the reconstructing or the synthesizing function is the same as the analyzing function, and that is what is reflected in 1b, and 1c gives me a Parseval's decomposition equivalent of the energy as we saw in the Fourier domain as well. So, things are much nicer when we make sure that the wavelets that I am looking at for different values of m and n are orthonormal. Now, let us move to scaling functions like the way we did in CWT, because we are going to talk about approximations a lot more than we did in CWT. So, we introduced scaling function way ahead in DWT. What is the role of the scaling function? It is exactly the same as in CWT. Recall from CWT lectures that the role of the scaling function is to construct an approximation. If you look at it from an approximation viewpoint, if you look at it from a filtering viewpoint, it acts as a complementary low pass filter to that of the wavelet filter, which is a band pass filter. So, either way it is complementing the wavelet function. It complements from a functional viewpoint, it provides approximations, whereas wavelets provide the details, and from a signal processing viewpoint, the scaling function acts as a low pass filter, whereas the wavelet acts like a band pass filter. So, we will look at the scaling function now, but with an additional requirement. Remember, we have just mentioned that orthonormal bases have certain advantages, which is that the synthesis equation becomes simpler, the energy decomposition is a lot more easier to interpret, and later on we will learn also that the calculation of the coefficients, whether it is scaling function coefficients or wavelet coefficients, they also become a lot easy numerically. So, we shall require that the set of the scaling functions and its translates. So, we are still looking at scale 1, that is m equals 0, exactly the way we did in CWT. When we introduced scaling function in CWT, we used the reference point s equals 1. So, here also we are using the reference point s equals 1 and denoting the scaling function by phi of t, now additionally requiring that at this scale the scaling function and its translates constitute an orthonormal basis, and that is specified in equation 2. The delta here is the standard Kronecker delta function, which assumes a value of 1 when the index is 0 and 0 otherwise. So, again as in CWT, we can say that transforming x of t with this scaling function and its translates essentially constructs an approximation or a low pass filtered version. We call these coefficients now s as s at 0 comma n. 0 stands for the value of m, because we are looking at scale 1, m is 0 pretty much, and then the population index being indexed by n. So, this you can say is the discretized equivalent of s of omega comma s comma tau, the way the continuous wavelet or the continuous wavelet transform equivalent of the scaling function that we saw in CWT. So, what is this here? It is simply the transform of x of t with phi of t minus n, again the same way as we have seen in CWT. When I try to recover the signal from the scaling function coefficients, then what I end up with is an approximation of the signal. Why do I end up with an approximation? Look, I am transforming x of t. If everything is perfect, then I should be able to recover x of t, but everything is not perfect here. Why? Because if you look at the top of this slide, we have assumed that the signal lives in the real dimensional, in the real space, but in this L2R, actually it should read L2R, what this means is finite energy signals in the real space. What about the scaling functions? What space do they span? Do they span the entire real number space? No, not really, not necessarily. They span a subset of the real number space, and we denote that subspace by V naught. So, phi t and phi of t minus n, this entire family span only a subspace of the real number space, whereas the signal itself lives in the larger dimensional space, which is the full real number space. Therefore, when I am computing the coefficients here, what these coefficients are essentially is resulting from projecting the signal onto a lower dimensional space. So, x of t lives in a larger dimensional space, phi of t lives in a lower dimensional space. Therefore, when I recover, obviously from those coefficients I am going to lose out the information. So, it is like this. As an example, I am walking on the road. Any person who is walking on the road is a 3-dimensional object from a vector algebra viewpoint, from a topology viewpoint. When you look at the shadow of this person on the road or on the wall when light is impinged on that person, then the shadow lives in a 2-dimensional space. So, what is being done is that the 3-dimensional object is being projected onto the 2-dimensional space, not that here phi of t actually spans the 2-dimensional, but the example essentially says that you are projecting an object which lives in 3-dimensional to a lower dimensional space. So, I give you the shadow. Now, if I ask you to recover the 3-dimensional figure just from the shadow, you will obviously not be able to recover the 3-dimensional object, but only an approximation of that. So, that is what exactly is happening. So, x naught of t is the approximation of x of t at scale 1 or m0. if I want perfect recovery, then I need to have basis functions that also span the entire real space, and we will talk about that. So, now I can extend this idea of approximation to a general reference point, exactly the way we did in CWT. We started off with a reference point being S equals 1, and then we said we will look at now an arbitrary reference point S equals S naught. Now, m naught is the corresponding reference point for me. So, S naught is 2 power m naught. So, what I do here is, first if you look at equation 4, now I am expressing x of t as a sum of its approximation at scale 0 and all the details that are left out in this approximation. Right. So, here we said in equation 3, I only obtain an approximation of the signal at scale 0 or scale 1. What about the details? Well, the details are contained in these wavelet coefficients at finer scales. Remember, the approximation at scale 0 is an aggregate of all the details at coarser scales, right. So, let me just show you graphically. So, if I just consider this scale, let us say this is a scale space, our reference point is S equals 1 or m equals 0. What my scaling function is doing, so let us say here is my scale 0. What my scaling function is doing is, it is actually constructing an approximation of the signal at by aggregating all the details that you would have obtained using the wavelet basis functions at larger scales, right. So, there are many wavelets here. I can say S m comma t, m comma n t, where m runs from 0, 1 and so on, right. And here m actually assumes negative values, because S is 2 power m, remember. If I want S less than m, so S than 1, so this is the space S less than 1, which means m actually is less than 0. Here I have -1, -2 up to minus infinity. That is what, those are the values of m spanning this space here. All these wavelets are that at levels m 0, 1, 2 and so on are being replaced with a single phi of t, which is at scale 1 or m 0. So, we call this as phi naught of t, right. And in fact, we also allow translates. So, t minus n, or you can say phi naught n comma t. So, that is what is happening right now. When I look at the approximation x naught of t, then what essentially it contains is, it contains all the details in these scales, but if I want to recover x of t fully, then I need the details or the projections on these scales as well, because then only together you can they constitute the basis for the real space, that is psi m n comma t, m belonging to the integer space, that is m running from minus infinity to infinity, and n belonging to the integer space is a basis. This entire family is a basis for the real number space which have finite energy, or that is the vector the functions in the real number space in the real space which have finite energy. By selecting only those wavelets corresponding to m greater than or equal to 0, what essentially I have done is I have chosen a subspace, I have only chosen a subspace here. So, phi of t or phi naught n comma t is an aggregate, it is equivalent to with only m belonging to z plus, right. Obviously, what I have done is I have taken this huge infinite family which spans the real space, and I have taken only some members of this family and constructed a scaling function. Therefore, this phi will span V naught, it spans V naught, which is a subspace of R or L to R, you can say. Normally we just sufficient write R at this moment. If therefore, if I recover x of t only from the projections onto this, I recover only an approximation. If I want to recover x of t completely, I need the other wavelets, the projections of the signal onto other wavelets which I have left out, which is for m belonging to, in fact it should not be z plus and 0. So, I need the wavelets that belonging to that that are spanned by allowing m to take on values in the negative integers space, that is m starting from -1, -2 up to minus infinity, all right. And that is exactly what that equation at the top is telling you. It says that to recover x of t, I need the projections or the coefficients that I obtain, not necessarily projections, the projection coefficients that I obtain with the wavelets at the remaining scales or at finer scales. Remember, as m with respect to s equals 1, whenever m takes on values 1, 2, 3 and so on, then we are looking at coarser scales, and whenever m takes on values of -1, -2 and so on, then we are looking at finer scales. So, I am looking and now to using the coefficients at finer scales to recover x of t. Now, if I choose an arbitrary reference point m naught, then I get to equation 6, where what I am doing is here I am introducing s of m naught comma n. Earlier my m naught was 0 in the previous equation. Here in equation 3 m naught is 0. Now, we have shifted from m equals 0 to m equals m naught. So, I have s of m naught comma n times phi m naught comma n of t. So, my phi of m naught comma n of t is once again representing all the wavelets that are at scales higher than or greater than or equal to 2 power m naught. And obviously, once again if I want to recover x of t, then I need the information at finer scales, finer than m naught. If I choose to ignore the second term in equation 6 and only look at the first term, then I end up with an approximation of x of t at scale 2 power m naught or at level m naught. And that is the basic idea in the equations that you see here. The message, the basic message from these equations is that the wavelet transform coefficients, which are the t's, your t of m comma n, at any level m, what do they contain? How do you interpret them? They contain the details required to move from an approximation at level m to level m minus 1. This is a statement that we made at the beginning of this lecture. So, to understand this point, let us look at the inner summation here at a specific scale m, and we shall call that as d subscript m of t. Now, what is this d subscript m of t? Momentarily, when you are looking at equation 6 here, particularly the second term, how do you evaluate? You fix a value of m and then you evaluate the inner term. Then you take the next level m and then you evaluate the inner term, that is how you proceed. At any level m, when the inner term is evaluated, what you are doing is you are recovering the detailed component of that signal at that scale. That is what it means, that is at scale 2 power m. And when you put together all those details at finer scales than m naught, then you get all that complementary information that was not present in your approximation at scale m naught. So, the inner summation is always going to give me the detail at that scale m or at level m, and of course, by our previous notation we call this summation, that is the first term here in x of t, as nothing but approximation at scale 2 power m or at level m. Why is this? Because we are going by the same convention here. When our reference point was m equals 0, we said whatever I recover from the scaling function coefficients at level 0 is only going to be an approximation at level 0. Now, since we have chosen an arbitrary reference point and that reference point is either m naught or m, whatever I recover from the scaling function coefficients is simply going to be an approximation at that scale m, 2 power m or at level m. We shall use this term scale and level interchangeably, but you should understand that scale is exactly 2 power m and level is m. So, please do not get confused. Now, with the introduction of these terms, I can write equation 6 as a m naught of t, that is approximation at a scale m naught or a level m naught, plus all the details at scales finer than m naught. Now, if I write this equation at two different values of m naught equals m and m naught equals m minus 1 and subtract, then what I end up with is x of x hat of m minus 1, x hat of t at m minus 1 is x hat of t at m plus dm of t. How do you get this? Well, as I said, write your equation 8 at two successive scales. So, I have x of t as x hat of t at m naught. Let us choose two different values of m naught equals m and m naught equals m minus 1. That is, I can choose two different reference points. If that is the case, then the first equation yields approximation of x at level m plus the summations that you have starting from m equals minus infinity to m dm, and then when you have m naught equals m minus 1, the breakup of the signal is x hat of t at level m minus 1 plus sigma m equals minus infinity to m minus 1 dm of t. All right. Well, if you are confused with the index, we can change this to L, so that it is a lot more clear to you. They are just dummy variables anyways. So, now when I subtract these two, so here, then what I get is, of course, on the left hand side I have the signal, so that goes to 0, and on the right hand side I have x hat of m, x hat of t at m minus x hat of t at m minus 1 plus sigma L equals minus infinity m dl of t minus, here I have m minus 1 dl of t. This entire thing is 0. So, I have just flipped the sides, because x of t minus x of t is 0. As a result, what I have is x hat at x hat of t at m minus 1, that is approximation of the signal at level m minus 1 is the approximation of the signal at level m plus dm of t. This is the fundamental equation for multi-resolution approximation. That is, why is this a fundamental equation for MRA? That is because as I move from m to m minus 1, the resolution is improving, because the scales are becoming finer. Therefore, the time grid now is much more finer than at m. In fact, it is finer by a factor of 2, right. So, what this equation tells me is the approximation of the signal at resolution 2 power m minus m minus 1, resolution is always the inverse of scale, or you can say the approximation of signal at 2 power m minus 1 is nothing but the approximation at a coarser scale, which is 2 power m, plus the details which are obtained by projecting the signal onto the wavelets at that scale. When you put them together, you get a better approximation. So, now if I can apply this recursively, I can say x hat of t at m minus 2 is x. Remember, associated with this approximation is a detail dm minus 1 at that scale. So, when I look at x hat of t at m minus 2, that would be, if I rewrite this equation, I would have x hat of m minus 2 of t as x hat of t at m minus 1 plus dm minus 1 of t. What is this dm minus 1 of t? Whatever details that you have obtained by projecting the signal onto the wavelets at this scale or at this level. When you put together this, you get x hat of m minus 2 of t. When do I recover the signal at all? Will I ever recover the signal? Yes, if I consider all the scales, which is actually the equation that we have seen earlier, 4 or even equation 6, so to speak. If I want the complete signal, then I need to consider all the scales, right, because only then I would have considered all the basis functions that span the real number space. So, let us now look at an example of multi-resolution approximations. That is, now what we are going to, what we just said is, I can now construct approximations of signal of a given signal at different scales, from fine to coarser scales. Why do I talk about only fine to coarser scales? Let us look at this example here. So, what I have here is a sine wave, and I want to construct multi-resolution approximations of this. What is exactly MRA? We will try to now understand this with a figure, and then with this example, and then look at the formal theory. First of all, I show you the sine wave in blue color here, which is at the left top. Although I show this as a continuous signal, strictly speaking, I have only samples of x of t at a sampling interval Ts. Okay. So, ideally I should be showing you spikes, right, but because the plot may look a bit uglier, I actually have not shown you that. But for all our discussion, x of t is not a continuous time signal, it is a sampled signal. Now, I do not have x of t at all until now, until the equation 9, we have been discussing with respect to theoretical signals x of t, but in practice I only have sampled signals. So, how does the situation change? Well, it does not change much, but just for one important thing, which is I have a bunch of numbers, which is the sampled signal. Now, what do I assume these numbers to be? That is, at what resolution do I assume to be? At what scale do I have this? Because if I look at a theoretical analysis, x of t is at the finest scale, because it is a continuous signal. Whereas now I am looking at a sampled signal, I cannot say it is at the finest scale. Had I sampled faster, then I would have obtained better x of t, that is better resolution. Had I sampled even faster, then I have even finer scale representation of x of t. But now I have decided on some sampling interval, therefore, I have x of t at some scale. The nice thing is, I do not really need to worry what scale this is. We will arbitrarily say, and we can do that without any loss of generality in the sense of our theory, that we will say that the sampled signal is available to me at scale 1, that is at m equals 0. I cannot get a better representation of the signal unless I go back and resample. So, now what all I can do is I can only construct approximations of the signal at coarser scales. In fact, the crudest approximations would be to simply downsample. What kind of approximations? Multi-resolution approximation. Now, I am interested not in some arbitrary approximation, I am interested in approximations that are at coarser and coarser time scales. Multi-resolution approximations are specific approximations where the resolutions fall by a factor of 2. So, I have the signal at a resolution of Ts in time. Now, the next resolution that I can look at is 2Ts, because we are looking at dyadic scales, or and because the resolution is inverse of scale, I can move from Ts to 2Ts. As I said, a crude approximation of the signal would be of the signal at a resolution 2Ts would be simply to throw away every sample, right. So, let me just show you that on the board and then we will come back to that example. Suppose I have a sequence x of 1, x 2 and so on. Let us say I have a bunch of samples like the one that I have here for the sine wave. Then this is at a resolution 2Ts, although I write x of 1 here, what this means is I have x at, in fact I can say x of 0, x of 1, x of n minus 1 if you like it. Then this is at x 0, x at Ts and x at n minus 1 Ts. Notice that I move from square brackets to parenthesis the moment I move from sample indices to actual time. So, this is at a resolution Ts. Now, I want to construct an approximation of the signal at 2Ts. So, the next resolution I am looking at it is a coarser resolution 2Ts. As I said, a crude way of constructing an approximation of this signal at this resolution is to throw away every other sample, right. So, I would have for example, x of 0 and then I have x of 2 and so on. Maybe let us assume that n is a power of 2, therefore, I have here x of. So, the previous sample would be x of n minus 3, nothing in between. So, I have thrown away, but this is a crude approximation. The approximation that you see on the figure is a better approximation than this one, and I will tell you better in what sense. A better approximation is to construct an average of x 0 and x 1 and say that over this interval 0 to 2Ts. So, here I have x of 2. What I am going to do is this x of 0, if I were to plot, I have 0 Ts and then 2 Ts, 3 Ts and so on. This is my time t. What I am going to do is I am going to say that an approximation of the signal at 2 Ts would be average of x 0 and x 1 and held constant over this. So, this would be the value here initially, right. In fact, in the example, that is what you see in the second plot. You can see now that we have plotted this as a piecewise constant over the interval 2 Ts. And again over the next coarser interval I would construct an average. So, I would construct an average of x 2 and x 3 and continue in this fashion, right. And this is how I continue, and when I want to construct the approximation at a coarser resolution, that is, now remember the resolution should fall off by a factor of 2. So, the next resolution that I am going to look at is 4 Ts, and so that is what exactly I am doing here. So, I am taking a sine wave at resolution Ts and then the next coarse approximation is at 2 Ts and then 4 Ts, then I have 8 Ts, 16, 32, 64, 128. As I move down the approximations, the resolution, the approximation becomes coarser and coarser, as you can see. In fact, the crudest approximation is simply the average of the sine wave over that entire interval, right. That is the crudest representation that you can give for the sine wave that has been sampled at Ts. So, here I am constructing averages over intervals of 2 Ts, here I am constructing averages over 4 Ts interval, averages over 8 Ts, averages over 16 Ts, that is why it is constant for a longer period of interval, then averages over 32 Ts, I have 128 points. So, here the signal becomes more and more piecewise constant over larger intervals, and then I have here over 64 Ts and 128 Ts. So, what you have now from all the signals that you have here, all the approximations that you see are constitute what are known as multi-resolution approximations. What is special about this multi-resolution approximation, as you go down you are actually constructing resolutions that are nested, that is that are embedded, or you can say the first feature is that the resolution falls off by a factor of 2. The other important feature is that the approximation that I have generated, for example, if I look at the red one, that is the 1, 2 plot, that has been constructed from an approximation of x of t. Remember, your sampled signal is also an approximation, and we said this approximation is at scale 0 or scale 1 or m0, level 0. So, the approximation at level 1 is derived from level 0, the approximation at level 2 is derived from level 1, and so on. So, one approximation is derived from the other and they are said to be nested.